data and cybersecurity threats from electric mobility charging infrastructure. The electric mobility charging infrastructure sector is growing exponentially with hundreds of thousands of new EV chargers connecting to critical energy infrastructure globally. In parallel, new heat pumps, renewables, batteries, and more distributed energy resources are added. EV charging infrastructure is a very particular new energy asset. Why? Charging infrastructure is located at various different residential, commercial, and public places. There are different types of low power and high power chargers. For example, DC fast chargers, extreme fast chargers, and megawatt charging systems. It creates a significant amount of new demand for load, can be X times more for a single location. It has volatile demand profiles, and there is an increased predictability over time associated with this infrastructure. And it can support the grid via storage and vehicle-to-grid options. Because of these particularities, this infrastructure provides several interesting functionalities and capabilities to the electric power system, for example, grid management and load balancing. EV infrastructure communicates with the grid and helps to prevent congestion. It supports renewables, for example, to use green electrons in time of overproduction, virtual power plants, storage, and more. With the rise of EVs, increased interoperability with the energy infrastructure, for example, the distribution grid control room, is a must, especially for high-power charging, and an increasing dependency from digital technologies is obvious. This will increase the vulnerability and open new pathways for malicious actors to attack critical energy and transportation infrastructure. Some of the vulnerabilities for digital attacks is caused by the complexity of different hardware and software components that make up the EV infrastructure ecosystem. This is an extensive list and includes EVs and their batteries, charging and car apps, EV chargers, metering equipment, communication equipment, charging control systems, switches, controllers, clouds, grid connections, and integration and network management systems. Charging infrastructure security, therefore, is a significant challenge. Most of these components are exposed to an ever-evolving list of attacks such as malware, ransomware, insider threats, spoofing, tampering, supply chain vulnerabilities, and more. This can have severe negative consequences for businesses, customers, and infrastructure such as service disruptions, financial loss, data and privacy breaches, safety risks, grid instability, damaged hardware, and more. Latest research suggests that there is an incomplete industry understanding of threat vectors, the attack surface, connections, and unsecured interfaces in EV charging infrastructure. Also, significant knowledge gaps concerning these risks are observed. The research even identified weaknesses and security concerns appearing in the communication-focused ISO 15118 Electric Vehicle-to-Charger Interface Standard and the underlying public key cryptography and public key infrastructure components. It also identifies that data security is not extensive. To make things even worse, the cryptography deployed today is not quantum safe and cannot be replaced easily. There is limited crypto agility. In addition to the known security concepts such as encryption, access control, and additional IoT-oriented concepts, zero trust-based secure system approaches following the NIST guidelines should also be evaluated. These are based on device-oriented approaches, adding additional layers of security for these devices and the data they generate. Data needs full protection when at rest as well as when being processed. This is where the current approaches for EV charging infrastructure fail.